For Unit 1.2b's example, what we're doing is we are taking a look at an energy calculation that goes with the hydrogen line emission spectra that we talked about in the presentation. So the question is, what is the energy associated with one photon of light released at 656 nanometers when hydrogen is excited? And then there was a second question about green light, which we will get to in just a minute. So if we look, remember, the most important part with all of our problems is that we need to read the information that the problem is telling us. So it tells us that it says, what is the energy? So that is what we are solving for. We are going to be looking for E, or our energy. So that's what we need to find. And it says associated with one photon of light released at, we've got 656 nanometers when hydrogen is excited. So we have a wavelength here because it's in nanometers, and we know we need to solve for the energy. So if we talk about the energy calculation, it's delta E equals h nu. Delta E is energy, h is Planck's constant, which is 6.626 times 10 to the negative 34th. That's kind of tiny there. Joule seconds. And then the nu is the frequency that we talked about. Okay, so if we look at that, we need two things to find our energy. We need Planck's constant, which is a constant, so that's good. We can solve that. And then we need the frequency. However, they only give us the nanometers, which is the wavelength. So you say to yourself, that is not particularly useful because I don't have a frequency. Fear not. We know that if we take the speed of light is always equal to the wavelength times the frequency. So if we want to find the frequency for this problem, we can do that if we are given the wavelength right here. So that's what we're going to do. We need to find our wavelength, use our wavelength to find our frequency, and then find our frequency and plug it back into this problem. So it's actually a two-part problem. There's kind of a lot going on here. So if we take our equation, C equals wavelength times frequency, I am looking in this case for my frequency, which means I need to get my wavelength out of here, and that leaves me nu. It's a really corny joke. It says, hey, what's new? And then you say C over lambda. Ha ha ha. No, okay. So I'm gonna find my frequency here. Sorry, it's lonely over here. I'm gonna find my frequency by taking my speed of light, which is 3.0 times 10 to the 8th meters per second. If you don't like to write meters per second, meters/second, if that confuses you, you can write that as meters seconds to the negative 1 if that makes you feel any better. And then we are going to divide that by our wavelength. And so you say to yourself, I'm just going to pop the 656 nanometers in there and then it's going to work. No, it's not, because this speed of light is in meters, which means we need to get these nanometers here into meters to make this jive for this equation. So you say to yourself, Mrs. Ottimeyer, this is really uncool. Why are you making me do this? And I say, life is hard. So we have 656 nanometers. What we need to do is we need to convert that to meters. So 1 times 10 to the 9th meters is equal to 1, oops, I screwed that up, sorry. 1 times 10 to the 9th nanometers is equal to 1 meter. And that comes out to be 6.56 times 10 to the negative 7th meters. And now we're cooking with gas, and we can put this into our equation. So 6.56 times 10 to the negative 7th meters. If you think about the units, meter and meter cancel out. And if I put this into my calculator, I'm going to take 3.0 times 10 to the 8th and divide it by 6.56 times 10 to the negative 7th. Again, I use exponentials because it just makes things easier. So I'm going to get a frequency of 4.57. I'm going to cut that off after the 7 here, just so that I don't have this insane number. and that's times 10 to the 14th power. So my frequency is 4.57 times 10 to the 14th, and the units that are left on this are seconds to the negative 1. Okay, so I finally have my stinking frequency. I can put it into my energy equation. So my change in energy is equal to 6.626 times 10 to the negative 34th joule seconds. That is H, Planck's constant. So that is the number that you're going to use always. It's printed on your equation sheet if you need it. You are going to multiply that by 4.57 times 10 to the 14th seconds to the negative 1. What ends up happening is if I multiply seconds times seconds to the negative 1, they cancel each other out, and I'm left with joules, which is that unit we talked about for energy. So I'm going to multiply these two things together, and we'll get our answer. Every year, there's some sort of question about this on the AP exam. Every year. Even weird 2020 year, there was a question on here. So we need to make sure that we know what's going on so that we can figure these out. So in this case, my change in energy is equal to 3.03 times 10 to the negative 19th joules. Okay? Track back your work and see if it makes sense. I found my wavelength, put that wavelength into the equation, and got my joules. Places where this runs wrong, you don't convert the nanometers to meters. You're going to get some insanely huge number. If I'm being totally honest, I totally forgot to change it myself, and I got this crazy number, and I'm like, that does not seem right. And that's because it wasn't right. So you have to make sure you convert the nanometers to meters. You need to make sure that you get your frequency from your speed of light equation, and then you get your answer. This is for one single photon of light. If you have more, then you need to address that, which we'll talk about in the next unit. The next part of the question was asking if the green light would have a higher energy or a lower energy. So if you think about green light has a wavelength that is smaller, which means that, I'll put it down here. Okay, if we're comparing red to green, green has a wavelength that is smaller. Because C is a constant, it means my frequency needs to be higher. And in my energy equation, if I have my constant times a higher number, it means that my energy is going to be higher. And so that's why when we talk about rainbow colored light, red is the lowest light and purple is the highest as far as energy goes. If you find yourself having any more questions, please pop into a Google Meet and ask me some questions or shoot me an email and we'll get things cleared up. One thing that I want to make sure that you guys are clear on this as well is this kind of work here, mine's a little bit scattered in this situation because I was trying to fit it on a sheet of paper, but on your understanding checks, I'm going to be asking you to write pictures or write stuff and then draw pictures and then take a picture of your work and upload it into a form. So please make sure that you show units and stuff like that. If you just show numbers without units, you're going to lose points and then we're going to run into problems. All right, good luck.